Hi students, welcome back to a note set part 2 for Unit 11, Emission Spectra in the Bohr Model. Remember last time that we now have a sense of the history of the atom. We reviewed that and we talked about the nature of light and how light consists of a spectrum of electromagnetic radiation, and we were able to calculate the energy of a photon uh, in one of those spectrums. We focus mainly on visible light, but kind of kept in the back of our mind that it's much broader. Now let's take our understanding of the atom one step further and connect it to our understanding now of light. Niels Bohr was a Danish scientist, and the picture here shows what he did and what was interesting about his insight. He took a gas tube with hydrogen in it. He subjected the hydrogen gas to high voltage electricity. Now, the high voltage electricity caused the hydrogen atoms to become what we call excited. That means the energy of the electrons within the hydrogen atoms got promoted to a higher energy level. He then filtered that light emitted from the hydrogen through a single slit and shined that light through a prism. And upon being bent, as light does, if it's shined through a prism, it gets bent. He found that there are four distinct wavelengths of light that come from hydrogen. And it just so happens, if this is the whole visible spectrum of light, we found a sample of light at about 410 nanometers of wavelength, at about 434 nanometers of wavelength, so a purple light, a blue light. 486 nanometers puts it in the green range of light. And then way over here at 656 nanometers, a red stream of light, but only at those four distinct wavelengths. Other elements, as Bohr noted, it showed different wavelengths of light, not at 410, 434, 486, and 656. For instance, helium will give its own unique spectrum of light. And by the way, the plural of the word spectrum is spectra, which is why this note set is entitled Emission Spectra. Okay, what do we mean by an emission? Take a look at this. If you take energy and shine it in the form of light at a sample of atoms, some of the electrons are going to get promoted. They're going to absorb the energy that they're receiving and enter a new state. We call that the excited state. But eventually, after leaving the excited state, they'll fall back to what's called the ground state or unexcited state. Upon going from an excited state back down to ground, a photon, a particle of light of a specific wavelength, is emitted or sent out from the sample of atoms. Well, in Bohr's experiment, high voltage electricity caused the electrons of hydrogen to enter an excited state. The excited electrons then gave off their added energy as photons with specific wavelengths. In the case of hydrogen, it was 410 nanometers, 434, 486, and 656 nanometers. Here's another way to visualize this. We got the H's are the hydrogen atoms. So we're shining energy on the hydrogen atoms. Some of the hydrogen atoms become excited and promote their electrons to a higher energy level than what they began with. Now, not all of the hydrogen atoms have to do this. Just the ones that happen to have excited electrons would be the ones that emit photons when they go back to ground state. The excited electrons eventually would fall back to ground state, and upon doing that, they're emitting a photon of a specific wavelength upon returning back to ground state. In the diagram, the reddish H's are the excited H's. Okay, so big question. Why did the hydrogen sample in Bohr's experiment give off just 4 distinct wavelengths. Wouldn't it make more sense if it's, uh, you could think of it in a couple ways. You could say, look, it's just one type of atom, hydrogen, so shouldn't it just give off one wavelength of light? Why 4? Or another way to think of it is, hey, since hydrogen is absorbing all kinds of light, why wouldn't it then give off all kinds of light? Why wouldn't it give off, for instance, the entire visible spectrum? Well, Bohr concluded that those emitted photons reveal the energies of the electrons inside, something you can't see. It's way too small for even any of the microscopes that we have today to see individual electrons. But you can tell the differences in energy levels by observing the light given off from excited atoms. That leads us to Bohr needed to develop an entire new model of the atom to be able to explain this. So here are the central tenets of the Bohr model. And keep in mind, Bohr was working a couple hundred years ago, and scientists often looked for reflections on a small scale, what they could see on a large scale. So Bohr proposed that electrons orbit the sun in the same way that electrons orbit the nucleus in the same way that planets orbit the sun. In like Earth orbits the sun in a roughly circular orbit. And electrons would do the same thing around the nucleus within the atom. The electrons are only found at certain allowed radii, or radiuses plural, called energy levels. Just like the Earth has an orbit or a revolution path around the sun, and you can't, the Earth isn't going to just go anywhere. It's not going to collide with Mars or Jupiter. It has a certain orbit. Well, electrons do that too, according to the Bohr model. The farther away from the nucleus, the more energy the electron has. So if you're starting out near the nucleus, that's the lowest energy level. And then if you go certain allowed orbits outward, you're gaining energy. So his proposal was, upon being irradiated with high voltage electricity, electrons within the hydrogen atoms got promoted to higher energy levels and then subsequently fell back down to their ground state or lower energy levels. And so he gave the term ground state when electrons are in their lowest possible energy levels. That is when they are closest to the nucleus. Okay, what does that have to do with the different wavelengths of light? Take a look at this. At the very bottom of this diagram, it says ground state. And then if you go up one level, it says excited state. And you go up another level, and it just says another excited state, with energy increasing as you go up. Well, if the difference between ground state and the first excited state corresponds to a certain amount of energy that would give a photon of a reddish wavelength, which is a lower energy wavelength than other colors in the visible spectrum, then perhaps the difference between ground state and the second excited state would give you even more energy, and therefore a shorter wavelength, that would correspond to the purple light. So in the Bohr model of the atom, it's not the absolute energies of any excited state that's important, but rather it's the differences between the energy levels that correspond to the energy of the photons emitted. Only certain wavelengths of photons are given off, and those certain wavelengths correspond to the differences in energy that are found within the atom. Hence, why hydrogen has only 4 wavelengths of emitted light, at least in the visible spectrum, and you don't see those same differences in helium because, well, they have different energy levels in helium than in hydrogen. The way we designate the different energy levels in the Bohr model is within the lowercase letter n. So they'll label these as n equals something. So in n equals 1 means that's the first energy level from the nucleus. It's the lowest possible one. The second energy level is n equals 2, and so on. So n equals 1, 2, 3, 4. You can have, there's theoretically no limit to the number of energy levels that you could have. But realistically, ground state electrons, at least for the elements that we know of, don't go higher than n equals 8. Okay, so let's go back to hydrogen. You've got a nucleus in the middle, and take a look at each of these rings or orbits around the nucleus. The first one's labeled 1, the second one is labeled 2, the third one is labeled 3, the fourth one is labeled 4, the fifth one's 5, and so on. Well, what Bohr is saying is, look, the difference between one energy level to another might correspond to reddish light. And the difference between another energy level and the ground state, or any, really, this could be the difference between any two different energy levels in the atom. If the energy difference between those levels gives a photon that happens to be in the visible range of light, because that's all that humans can perceive, then you would be able to perceive that. In the case of hydrogen, the differences were 410, 434, 486, and 656 nanometers of wavelength of light emitted. And so Bohr observed a reddish, a green, a blue, and a purple for hydrogen. But take a look at this. Here's helium's emitted emission spectrum. Helium has a red, a yellow, a green, kind of like hydrogen, but then it has a darker green in indigo and a blue that's not quite the same as the blue from hydrogen, and there's no purple. For neon, neon has its own unique internal electron structure. It has 4 emissions in the red range of light, 2 in the yellow, and nothing else. Sodium emits just yellow light. Mercury emits yellow, green, darker green, kind of an indigo, and a blue and a purple, which are pretty close in wavelength. Every single element has its own unique emission spectrum. And you could think of it as like an atomic fingerprint. Now picture this, students. This is why emission spectra are so helpful for chemists. Let's say you're studying a compound whose identity you don't know. Well, what you can do is shine a bunch of light at that unknown compound. Study the light that's given off after the excited electrons fall back to ground state, and figure out, with the help of a computer most likely, what pattern of atomic signatures you have. And in doing that, you can say to yourself, hey, there's got to be some helium in this unknown sample, for instance, because all of the helium lights, wavelengths of light, are emitted from that sample. And it's very, very specific. So the difference, for instance, between hydrogen's blue and helium's blue, we would have trouble telling the difference with our own eyes, but a computer can tell the difference. So it's a very precise way of identifying an element. Okay, that's nice for theory, and that is the underlying theory. Now let's get to the work that's going to lead us to our homework assignment. So we're going to be drawing Bohr model diagrams. So that means we're going to be drawing a nucleus in the center of an atom, and then rings around the nucleus which correspond to the energy levels of the electrons. Here's an important rule. The first energy level, the first ring around the nucleus, which we label n equals 1, can only hold up to 2 electrons and no more. The second energy level, which we label n equals 2, can only hold up to 8 electrons, no more. And the third energy level, n equals 3, is going to hold the rest of all the other electrons. Now, you might say, but why don't you give me a number for the limit of n equals 3? Well, here's the nitty gritty is the Bohr model kind of breaks down as you get to bigger and bigger atoms. So for that reason, we'll never ask you to draw a Bohr model diagram for elements beyond element number 20. And so we're keeping it small atoms with small numbers of electrons. Okay, so with that, let's get down to some steps that we can take in order to draw good Bohr model diagrams for any atom that we're asked to. 4 simple steps. You'll be given the element's name. They'll say, draw a Bohr model diagram for phosphorus, for example. The first thing you'd want to do is find that element on the periodic table. Identify the atomic number, which is the number of protons. And then this is really important. Unless you're told otherwise, go ahead and assume that that atom is neutral. That means that you have the same number of electrons as protons. If we're talking about phosphorus, phosphorus has an atomic number of 15. And unless I'm told otherwise, I'm going to assume that it's neutral phosphorus. So it would also have 15 electrons, same number as the number of protons. Then we'll draw dots around the nucleus, and those dots will represent the electrons. Each ring drawn around the nucleus will be like an orbit in the Bohr model, where the first ring around the nucleus is n equals 1, the first energy level, and the second ring around the nucleus is n equals 2, the second energy level, and so on. Please be aware that we're only going to ask you to draw Bohr model diagrams for elements in the first 3 rows or periods of the periodic table. And the reason is it gets really, really complicated and tedious to draw large numbers of rings around the nucleus, and we can convey all of the understanding that we need just by keeping it simple and small in terms of atom size. So let's try this problem together. We're going to prepare a Bohr model diagram for the most common isotope of sulfur. If we go to the periodic table and look up sulfur, we'll see that it has an atomic number of 16, it has the chemical symbol S, and it has an average atomic mass of 32.065. Note, if we're asked to draw the most common isotope of sulfur, that means we would round that average atomic mass to the nearest whole number in order to get the mass number for the element. You would then, if you were curious to find the number of neutrons, you would then subtract the atomic number from the mass number to find the number of neutrons. But in this case, we're going to keep it really simple. The atomic number is 16. We're assuming that the atom is neutral, so there will be the same number of electrons as protons. So in this atom that we're going to draw, there are 16 protons and 16 electrons. We'll start by putting the element symbol in the middle of the diagram. And then around that, we're going to start drawing rings. Sulfur will take 3 rings in order to find a home or a place for all 16 electrons. Remember, the first energy level can only hold up to 2 electrons. Sometimes those are called shells. You can picture that as concentric rings around the nucleus. It's kind of like you're adding a new shell with each energy level. Well, of the 16, we can only fit 2 in the first shell, or ring, or energy level. You can fit up to 8 in the second ring, or shell. So if you add that together, that's 2 in the first ring, or energy level, 8 in the second ring, or energy level. That's 10 altogether so far. Well, the third energy level can take all of the rest. Remember, we had 16 electrons in total, not more than 16, but also not less than 16. So it's exactly 16 electrons that we need to draw. And you can do that by drawing a third ring. And that's it. That's all we're going to ask you to do for the homework assignment. In the homework assignment, there are all 18 elements in the first 3 rows or periods of the periodic table. Just follow these steps and you'll be able to do this just fine.